Hi, this video is about heating curves. What really happens when we're heating a substance? Well, this is a heating curve for water, and most heating curves have this general shape. So, as we can see here, on the y-axis, we have our temperature in degrees Celsius, and along our x-axis, it's kind of like time as time goes by and our heat that's being added. So, as you can see, we're going to start down here, and this would be below zero, so it would be ice. And we start adding heat, and as we add heat, as you would expect, the temperature goes up. But then it stops and it plateaus, it flattens out right here, it forms this plateau. So, what's happening at the plateau? There's no temperature change, that's why it's flat. The solid is still taking in energy, but what is that energy doing? The energy is being used to break the intermolecular forces in the ice. So the ice is melting. So we have phase changes at the plateau. So again, here we go. We had solid ice, and then we heated it up, and then here where it plateaus, that is a phase change. That is where melting is happening. And we know for ice that that is at 0 degrees. So it starts to melt. And so here on this plateau, we have both a solid and a liquid present. And that is the case until we get to here, till all the ice is melted. And then as we continue to heat, to add our heat, our temperature starts to go back up again. And so we have that upward slope. So now we're heating our liquid. So as we're adding that heat, we are increasing the movement and the kinetic energy of the molecules. Our temperature is going up, and then we hit another plateau. Well, just like that first plateau, there's no temperature change. That's that flat line. The liquid is taking in energy, but what's the energy doing? Remember, energy is the capacity to do work. What's it doing if it's not making the temperature rise? Well, the energy is being used to break the intermolecular forces within the liquid, so the water is vaporizing. Again, at this plateau, we have a phase change. We have vaporization going on. So, we ended here, and we had all of our ice melted. Then, as we added heat, we were increasing the kinetic energy of those molecules, our temperature was rising, and then we get right here and we see another plateau where our temperature is not changing. So these plateaus are phase changes. So this must be for water at normal 1 atmospheric pressure, must be 100 degrees Celsius. And what is present in this plateau is both a liquid and a gas until it is all vaporized, and then it turns into all gas. So once all the liquid is vaporized, the temperature again begins to increase. What we're doing is we are adding energy to our gas molecules. They are just moving even faster, and our temperature of the gas molecules is now increasing. So what you need to know on a heating curve. First of all, you need to know that at the plateaus where we have all of this, where the temperature is not changing, that is where we have phase changes. Where the temperature is not changing, that is a phase change. And during those phase changes, what is happening here when in our heating curve, you are breaking intermolecular forces. So you're breaking those hydrogen bonds in water, and you're breaking those dispersion forces and those dipole-dipole forces. So you are breaking the IMFs. And so then it's going from our solid to a liquid, and then from a liquid to a gas. So what you need to know is the plateau. Those are phase changes. And you need to know what phase there is during these sloped regions too. Here, when we're below the freezing point, it's a solid. When we are above the freezing point or the melting point, we have a liquid. And then when we're above the boiling point, we have a gas. And then at these plateaus, when we're between phases, you have both phases of matter present. Alrighty. We could also do this curve backwards. We could have started with a gas and cooled it down So we could have been removing heat, and then our temperature would be going down, and then we would have this gas condensing back into a liquid, and then if we cool it even more, here we would have it going down to a solid, and then it would freeze, and that's called a cooling curve when we read this backwards, but this is typically what they look like. All right, so here we just started our cooling curve a little above 0 degrees. So our liquid is cooled down when it hits our what we call melting point. It's also the freezing point. So the freezing point and the melting point are the same. When we get down to 0, what happens is our liquid starts to freeze. So we've got a liquid into solid here at this plateau until all of it's frozen, and then our temperature will continue to drop as we remove the energy from our system, and then we've got our ice. Well, there's something that's really cool. It's called supercooling, and what happens is if 0 is our freezing point, so this would be for water again, you know, we are at 4 degrees Celsius, our temperature is going down, 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 it's a liquid, the temperature goes below 0 and it's still a liquid. It's called supercooling, but then it comes back up to the freezing point of 0, and then it plateaus out here. This is called supercooling, when you dip below the freezing point and it still remains as a liquid. So supercooling is when you chill a liquid below the freezing point, but it doesn't form the solid. All right, well, we looked at a cooling curve in class. We're going to look at some freezing points and do some labs with this. Bye.